We're going to shift gears a little bit here now and talk not about friction per se, but about other forces, maybe including friction, but problems involving more than one force, multiple forces. Now, when we're solving problems that involve multiple forces, we haven't done that yet. We have to draw what we call a free body diagram first. That's going to set it up for us. A free body diagram is a diagram that shows all of the forces acting on the object. So for instance, if I'm standing on the ground like I am right now, or you're sitting in your seat like you are right now, there are two forces acting on this object, on this person. There's the force of gravity acting down, and there's an equal and opposite normal force acting up. Now, you could have drawn the normal force there, where I did, or you could have drawn the normal force up here. That doesn't really matter. Okay, what's important is that you draw the normal force and the force of gravity in the right direction, and that you draw them roughly the right length of vectors. Okay? What do I mean by the right length? Well, compared to the other vectors, the other force vectors, how long should they be? Okay, they should be drawn roughly to scale. All right, let's do another one. Let's say we got a car. It's on the road, driving on the road, but guy slams on the brakes. So there's a pretty big force of friction here, right? But there's also air resistance, a force of friction and air resistance. What do we got now? Well, we have a force of gravity acting down. We have a normal force acting up at 90 degrees. Notice I drew the normal force in a different place this time. That's okay, as long as I draw it the right length in the right direction. I've also got a force of air resistance pushing back. If it's moving to the right, then the force of air resistance would act to the left. And I've also got a force of friction between the brakes that's acting to the left. Now, how big is the force of air resistance from the force of friction? I don't know. We don't have any information to tell me. So we can't really draw those to a proper length unless we know their values. But we know their direction. We know they have to be opposite to the way that the object is moving. Assuming it's moving to the right, then these two forces have got to be to the left. What about this one? What about this one? You got a car on a hill like this. It's being pulled up the hill by a tow truck. But there's a force of friction that's opposing that motion. Let's draw the free body diagram for this one. Well, we know that we would have gravity acting down. Which way does the normal force act? 90 degrees. We know that we have an applied force. I'll call that FA. That's applied by the tow truck. I don't know what its value is. I don't know how long to draw it. We have a force of friction acting to oppose the motion of the car, which is always going to act parallel to the surface. So that would be my free body diagram for a car going up the hill. Sorry? Yeah, you know what? If there was air resistance, we'd add that in as well. It would oppose the motion. So we draw it like this. Free body diagrams show all of the forces acting on the object. Now, they may also show the mass of the object or the acceleration of the object or whatever, but they don't need to. They need to show the forces. They may show other stuff as well if you want. Why do we draw these free body diagrams? Well, you can imagine if you're solving a problem where there's 13 forces acting on an object, it becomes a lot more difficult to solve it using F is equal to m times a. What force do we use? Remember, F is the net force, but the free body diagram makes it a lot easier for me to find the net force. So here's the deal. Whenever you have a problem where there's more than one force acting, you got one force, just solve it the way we've been solving them with friction and other forces prior to that. But if you've got more than one force acting, then make sure you draw the free body diagram and then do something that you'll learn about in a couple minutes. Here's another quick example, and then we'll set you free for a couple of minutes on just a couple practice ones. A car with a weight of 10,000 newtons downwards is coasting on a level road. So here's the level road. Here's the car. It's not a very attractive car. It's kind of a boxy car, but it works. It's got a force of gravity or a weight of 10,000 newtons acting down. So let's draw that downwards now. What else can we draw? The normal force acts up. Same value, right? Because it's going to oppose gravity. Doesn't matter where I draw it as long as I draw it in the right direction and roughly the right magnitude, 10,000 newtons. All right, what else do I got? There's a force of friction of 500 newtons. It's going to act, assuming the car moves to the right, friction is going to act to the left. And its value is 500 newtons. Now, by rights, it should be a lot shorter than the 10,000 newtons, but I just didn't draw the 10,000 newtons quite long enough. Bottom line is, we can see that it's smaller than the 10,000 newtons. What else do I get? Air resistance. What's the force of air resistance? 2,500 newtons? Now again, it's going to act to oppose the motion. If the car was moving to the right, air resistance is going to act to the left. And it should be drawn longer than the force of friction and shorter than the force of gravity. This is not drawn to a great scale, but it becomes tough when you're dealing with numbers so dramatically different to do that. As long as you have them roughly right. Gravity is bigger than air resistance, which is bigger than friction, then we're good to go there. That's it. Any more? Nope. Now I'm going to show you something that you don't have to do technically as part of your free body diagram, but you are going to have to do it later on. We'll spend some more time on this after we master this free body diagram thing. Whenever we have two forces that will cancel each other out, I'm just going to scratch them out. Do we have anything that cancels each other out here? I'm going to cross those out because in the end, they're not really going to matter, right? The only two forces that are going to contribute to the motion of this car are the force of air resistance and the force of friction. All right, so here's what I'd like you to do now. Draw the two free body diagrams that are referenced in the questions on page 131. All right, question number 1 says the driver in example 3.1, and this picture that we see up on the board here is from example 3.1. This time he or she sees a pedestrian, slams on the brakes, still has that force of air resistance, same value, right? Air resistance isn't going to change just because we slam on the brakes, but the force of friction does change. Now the force of friction goes up dramatically. It better, otherwise that pedestrian is going to be in a lot of trouble if we're just going to allow the car to just slow down naturally. So how does this change? Well, everything is the same about it. Everything is exactly the same except this force of friction would no longer be 500 newtons. It would now be 5,000 newtons. And because it's 5,000, it should be a longer force, a bigger force than the force of air resistance. Again, by rights, these should have been bigger forces as well because that 5,000 force needs to be smaller than the 10,000 forces. All right? Take a look at question 2. A car moving at a constant velocity starts to speed up. The weight of the car is 12,000 newtons downwards. Here's the car. The force of gravity acting on the car, the weight, is 12,000 newtons. There's a normal force acting up that's also 12,000 newtons. There's air resistance that pushes it backwards. Moving to the right, air resistance will act to the left, and its value is 3,600 newtons. The force of the engine engaged, the force of friction exerted by the road on the tires is 7,200 newtons forward. How do you get a forward friction force? Yes, so the wheels turn, and the wheels on the road stick together. So the wheels apply a force on the road backwards, and the road applies a force on the wheels forwards. Okay, so you're going to learn about something called Newton's third law later on. Do you guys remember that from Science 6? For reaction is an equal opposite reaction. Okay, the wheels apply a force on the road applies an equal opposite force on the wheels. So it's going to actually be forwards. And its value is 7,200 newtons. So it's going to look something like this. Anything I could cross off there? Yeah, I could cross those off. They almost always cross off because they're almost always the same value. And that would simplify things. Now we'd be left with two forces, which is still more complicated than problems we've done until now. All the problems have involved one force. Now we get two forces. We got to draw the free body diagram and then do something else after that. Yep. Yeah, when we go to actually solve the problem, we would make it negative. Now the negative means direction, though, right? The positive and negative mean direction, and we have arrows indicating direction here, so it's not necessary to make that negative right now in the picture because the arrow is showing us that it's opposite in direction. Now, it's not wrong. It's okay to do that. Later on, when we solve this problem mathematically, then it becomes important, yeah, to make it negative value. All right, so what do we do with this? What do we do with these free body diagrams after we've got them drawn? Well, you guys know that when you have a problem involving more than one object or more than one force, you've got to draw a free body diagram and cross off anything that you can cross off. And then with what you have left, I want you to do the following. I want you to set F net equal to all of the forces that are acting. Maybe they're called F1, F2, F3. Maybe they're called FA, FF, FAir, whatever they're called. Set F net equal to the total of those forces, because that's really what net means, right? Total. Remember my net pay was the total of all the additions and subtractions to my pay. Net force is the total force. You guys remember what the total force is also equal to? Or what the net force is also equal to besides F1 plus F2 plus F3? How about M times A? So what I want you to do is, if you have more than one force acting on an object, just draw the free body diagram and then cross off things that you can cross off. And then once you've done that, with all the forces that are left over, as long as they're in one dimension, with all the forces that are left over, set F net equal to the sum of all those forces, and then set MA equal to the sum of all those forces. All right, so let's do one problem, and then I'm done for the day. This question on page 132 says, two people A and B are dragging a canoe out of the lake onto a beach using light ropes. Each person applies a force of 60 newtons forward, but there's a force of friction that acts backwards of 85 newtons. Starting with the free body diagram, calculate the net force on the canoe. Now we're looking at this canoe from above. That can make it a little bit trickier, actually, because when we're looking at it from above, it's difficult to draw the force of gravity and the normal force, right? Gravity would actually be acting into the board, and the normal force would actually be acting this way, out of the board. The good news is they're going to cancel. So we're not actually going to worry about drawing them in this case, okay, since they cancel it. We do know that we have an applied force, we'll call it FA, of 60 newtons forward. We know that we have an applied force FB of 60 newtons forward, or you could call that F1 and F2, Fx and Fy. We have a force of friction that acts backwards, and it's 85 newtons. Now I've got my three forces drawn. There is gravity, there is the normal force, but they cancel each other out, so we're only worried about these ones. Let's set now F net equal to the sum of the forces, FF plus FA plus FB. Now, we would usually set F net equal to M times A, but since we're looking for the net force, not the acceleration, I'm just going to sub in my numbers for these forces now. FF is 85, right? Sorry? Negative 85, good, because it's to the left. FA is 60 newtons. FB is 60 newtons. And what do I got here? Add these up, ends up being 35, I think, isn't it? 35 newtons. There we go. Listen, if we were looking for the acceleration, then we would have set that equal to M times A. Like I said back here, but because we're not, we'll just leave it as F net is equal to the sum of the forces. All right. Your homework that goes along with that is on page 132, questions 1 and 2. Both sets of homework that you've been assigned today, page 132, and the other one was page, I can't remember, page whatever it was assigned earlier here today. Both of those are due for Friday.